So today we're going to be looking at how we compare brightness of different stars. But before we do that, we need to introduce ourselves to a new unit of distance, and this unit of distance is called the parsec. So if we look at the sun and the earth, we know that the distance between the sun and the earth is 1.44 times 10 to the 11 meters. And this is also known as 1 astronomical unit, or 1 AU. And now let's say we have a point that is somewhere out here, such that if you were to connect these two lines together, this angle here is 1 arc second. And you might be wondering, well, what is an arc second? Well, 1 arc second is equal to 1 over 3,600 degrees. Now this distance here, if you were to do simple Pythagoras, and we're going to call this distance d, this distance d is equal to 3.01 times 10 to the power of 16 meters. And this is known as 1 parsec. And you can get this using trigonometry, where 1 parsec can be shown to be equal to 1 AU over the tan of 1 arc second. Now sometimes in the exam they may ask you to draw a diagram to represent the definition of a parsec, and this here is what you are expected to draw. And now the literal definition of a parsec is the distance from the sun where an observer observes at an angle of 1 arc second. So now that we've introduced you to the idea of a parsec, let's now discover how we can compare brightnesses of different stars. Now the first kind of brightness is called an apparent brightness, or we're going to call it the apparent magnitude. And here magnitude and brightness can almost be used as the same thing. And what this apparent magnitude is, it is the brightness of a star as seen from the Earth. So if I were on Earth and I were just looking out into the sky, how bright I would see a particular star is what is defined by this apparent magnitude. Now, in the old days, I think people started viewing stars and the brightness of different stars from around the era of Greeks or something. So they came up with a scale where 1 is a bright star and 6 is a very dim star seen from the Earth. And a star that has a brightness of 1 is 100 times brighter than a star with a brightness of 6. And at the time, they just simply made the scale by just looking out in the sky using their naked eye and comparing the different brightnesses of stars. So the scale will go from 1 to 6, and you have like 2, 3, 4, 5. And the difference between each of these is a factor of 100 to the power of 1/5. Or in other words, this is the 5th root of 100. And the 5th root of 100 has a value of roughly 2.51. And what this means is a star with a apparent magnitude of 2 is 2.51 times dimmer than a star of apparent magnitude 1. And the same goes, a star of apparent magnitude of 4 is 2.51 times brighter than a star of apparent magnitude 5, for example. Now this was the old scale, but nowadays our scale probably goes from around -40 to 40 or something like that. But even with this new scale, let's say we went from like 11 to 12. 11 is 2.51 times brighter than 12. So we've looked at the apparent magnitude, so now let's look at something called the absolute magnitude. And the definition for the absolute magnitude is the magnitude of a star if it were seen from a distance of 10 parsec. Now, what this definition means is, let's say I had a star somewhere super far out into space. If I were to then bring that star from wherever it is all the way back to 10 parsec away from the Earth, what would be the apparent magnitude of that star? So if we were to compare the absolute magnitude of all these stars, we're basically going to put every single star that we know 10 parsec away from the Earth. So that means the sun or some random star far out into the far and deepest end of the universe. If we're comparing the absolute magnitude, these are going to be seen from the same distance. And what's useful about this is it basically tells us how much power or light a star is actually emitting. And just like the apparent magnitude, a star with a brightness of 1 is 2.51 times brighter than a star of absolute magnitude 2. That means if something has an absolute magnitude of 1, if we were to place that at a distance of 10 parsec away from the Earth, it would be 2.51 times brighter than a star of absolute magnitude 2 if we were to put that second star at a distance of 10 parsec away from the Earth as well. We're going to call this apparent magnitude, or we're going to denote it by a little m, and we're going to denote absolute magnitude by a capital M. And what we can actually do is we can relate these two together. And we can get an equation where m minus big M is equal to 5 log d over 10. And d is the distance of a star from Earth. And this is given in the unit of parsec. Remember, little m here is your apparent magnitude, big M here is your absolute magnitude. And as I said, this d here is the distance of a star measured in parsec. Remember that has to be measured in parsec. That is the important bit. Now we're going to be looking at something called a type 1a supernova. And there are many different kinds of supernova out there. And later when we look at how different stars evolve, we're going to be introduced to a different kind of supernova. But this type 1a supernova is actually something quite special. Now, how does this type 1a supernova occur? Well, it starts off with a small star. And this kind of small star can be noted as something called a white dwarf. And this small star and this giant star that we're going to have here, they are going to be orbiting around each other, around some common points. So these stars are going to be orbiting around each other. This here is known as a binary star system. Now this small star is typically known as a white dwarf, and this giant star may be a red giant, but it could be any giant. And these two are kinds of stars that we will be introduced to later on when we talk about the evolution of different kinds of stars. And what's going to happen is this red giant or this giant star is going to have a lot of material on the outside. And because of gravity, as we know, this material is actually going to get attracted to this dwarf star. And what you'll see is this giant star's material will actually start to form a spiral around this small star. And you'll see there's a lot of material being accreted around this small star, as the gravitational attraction from this small star is just pulling and pulling a lot of material from this massive giant. And as more and more of this material excretes around this small star, it becomes unstable and explodes in something called a type 1a supernova. What is so special about type 1a supernova is that they are something called standard candles, which means that we know the exact absolute magnitude of these type 1a supernova. And what's special about knowing the absolute magnitude is that if you measure the apparent magnitude from Earth, we can then therefore determine the distance from this type 1a supernova and the Earth. And let's say this type 1a supernova was occurring in a particular galaxy or particular region of space that we wanted to examine. We can then have a rough estimate or actually a pretty reasonable estimate of the distance from this particular galaxy or whatever we're examining from that galaxy to the Earth. And that's why phenomenon like Type 1a supernova are very, very important. So if we were to measure the absolute magnitude of a Type 1a supernova over a particular amount of time, we would figure out that it would form this kind of graph, where it peaks at a value of around minus 19. And in your exam, you can probably have this value ranging from anywhere from minus 18 to minus 20. And remember that for absolute magnitude, the lower a value is, the more bright the phenomenon is. So actually, the values here will actually increase. So this here might be like minus 12 down there, which might be strange to you at first because you're used to bigger number being on top. Now I've centered this graph such that the peak lies at 0 days. And this is something that we typically do. Now technically the Type 1a supernova first explodes at this point here, but we always use that peak is at 0 days. So this technically happens at some sort of like minus 20 days, or I don't know, something like that. Now this is the absolute magnitude versus time graph for a Type 1a supernova, and you may be asked to recall this or draw it in an exam. Now the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.